Okay, so in lecture 16, we're going to introduce the rule of proof called universal introduction, UI. Universal introduction. Now, as you may have guessed, so as with the rules for the propositional connectives, we had an intro and a lim rule for each connective. So for example, we have and elimination that lets you take a conjunction and take off the conjuncts. And we correspondingly have and introduction where you take the conjuncts and you put them together. Now, previous lectures, we had universal elimination that allows you to go from a universal sentence and derive an instance of the universal sentence. So universal introduction will let us reason to a universal sentence. However, you should be on the edge of your seat because that seems like there's no possible such rule, because how could you go? You can't go from an instance to a universal. You can't go from the statement, Professor Halverson teaches logic, and then say, every professor teaches logic. That's obviously not valid reasoning. So how could you end up with a universal sentence? That's the big mystery we need to solve here. So in symbolic form, what does it take to show for all x, phi x, where phi x is any complex predicate phrase that says something about a thing? Okay, so it could be as simple as px, but it could also be a very complicated thing. But how do you show for all x, phi x? How in the world could you do that? Okay, now the truth is, in one sense, this is lost in the sands of time. We don't know exactly how this occurred to human beings at some point in our ancient prehistory. But the truth is, it's one of the most incredible basic thought inventions that humans ever had. The basic thought invention is we can, in some sense, imagine an arbitrary thing. So how can we do that? Because if you imagine a thing, you imagine it with specific characteristics. So the idea is you pick an arbitrary name. So in the slide here, I've just used little a. So you say, let A be the name of anything. I don't know what. Now, if you can reason to the conclusion that phi A, that is phi is true of A, this predicate phrase phi, then you may infer that phi is true of everything because A was arbitrary. That's the key underlined in purple here. If you can demonstrate phi A independent of what A is, so in other words, you don't use any information about what A is, and you're able to show phi A under those conditions, you may infer, this is universal introduction, you may infer for all x phi x. Okay, now it's not like you've never seen this before. In fact, all of you have already in your academic careers used this kind of reasoning in many contexts, but also in particular in, say, geometry. So in geometry, anytime you say prove something about all triangles, you're doing this. And what you do often is you'll say, you pick a name like A here in blue for an arbitrary triangle. You'll prove something like the internal angles of A add up to 180 degrees. So then what you infer is anything that's a triangle has that feature. So as I've written down in this sentence on this page, any triangle, anything, if it's a triangle, then it has the feature phi, where phi here I'm taking to be has internal angles summing to 180 degrees. Okay, so now we need to formalize this notion, because to do it properly in symbolic logic, we need some kind of control over the notion of we didn't use any specific information about A. So how do we do that? That's the big question today. So what I'm going to do is I'm going to actually just start with an example, and I'll explain through this example what the rule is. Okay, so here's what we want to show. Now, this is obviously something that we should be able to show. We should be able to show that from the premise, everything is f and g, conclusion, everything is f. In fact, you might be tempted to say that should be a rule. That should be a rule that you can always infer everything is F from everything is F and G. But remember, we want not to multiply rules. We want to keep our set of rules very Spartan and then prove things. So we'll use our proof rule of universal introduction to prove this. Okay. Okay, so now what I'm going to do is I'm going to, on line 2, I'm going to simulate the talk of let A be an arbitrary thing without actually writing that. There's no place to write that in my proof. But what I'm going to do is I'm going to infer from line 1 that A, which notice A hasn't occurred before in the proof. So A is just a name I know nothing about. I'm going to infer that A is both F and G. So that follows from 1 universal elimination. Okay, now the key at this stage, at step 2, is if you look at what's on line 2, it says FA and GA, and you look at what that depends on. It depends on line 1. Line 1 says nothing about A. So what I've done now is I've inferred something about A from things that don't mention A. So whatever I've inferred here should hold for anything because it didn't matter that it was A. This would also be true of B or C or whatever. Okay, so now comes the new rule. The new rule says, well, actually, first I need to get my FA out. So I'll go ahead and use propositional logic to and elimination to get FA. Okay, now, normally you can't infer from FA to for all X, FX. That's not legitimate. However, in this case, looking at the fact in this line here, line 3. So this is where it's key that line 3 is not a flat out assertion FA. Line 3 says FA follows from line 1. Line 1 doesn't mention A. So it's saying in principle, line 3 is saying FA follows regardless of what A is. So then we're given permission to write for all X FX. So we are, let me put this in black. So there we're generalizing the rule. It's going to look, line 4 is going to look like there's no, like this rule is far too libertarian because what it looks like is from line 3, I can just throw on for all X, replace the A with X, copy down the dependency number and say universal introduction. However, there's a restriction here. The fact is the restriction, which I have obeyed, is this only is permitted, what I just did on line 4, is that name A on line 3 cannot occur. The instance in FA, the instance FA, A cannot occur in the dependencies. A does not occur. So 1 here, the dependency on line 3 is a tag for this sentence back here on 1, on line 1, the sentence for all X, FX, and GX. That doesn't contain A, so the restriction is satisfied. Okay, so here is a symbolic representation of what I just said. So the restriction on UI, universal introduction. So in general, the rule works like this. From line M to line N, you may from an instance phi A, so phi A is an instance of phi X. It's an instance with the name A. You may go backwards from phi A to for all X phi X, copy the dependencies down as I've done here. So delta beside line M and beside line N is a list, any list of dependencies. I just copy those down. And then crucial in red there, the restriction is this rule may only be, this move may only be performed if A does not occur in the dependencies delta. Now, delta in our proof format is a list of numbers. What that means is A does not occur in the sentences that are in those lines, okay? Nor can it occur A cannot occur in the formula phi itself. If you wonder how could that happen, wait just a second. I'll give you an example, the second example below on this page. Okay, so let's look quickly at two cases where the restriction is violated. So these proofs in red, quote unquote proofs, are actually incorrect. So these are cases where it's not done correctly. So in the first case, from here, line 1 to line 2 goes from FA on line 1 to for all x fx. But look at line 1, the instance on line 1, FA, it depends on what? 1. Does the name occur? But the name A occurs on that line. So you can't go from line 1 to line 2. That's not permitted. Okay, next example. And here we actually see a case, this next example below, of a relation symbol. So here R is a relation symbol that has two blanks. On the first line here, both blanks have X. So what line 1 says is for all x, R, X, X. So in other words, for everything, the relation R holds between that thing and itself. Okay, the first step here of UE is permitted for sure. So going from line 1 to line 2, going from for all x, RXX to RAA is permitted. However, what you now have is if you try to go from RAA and do universal introduction, what you're actually doing if you do that is you're treating the phi that you're generalizing. So if you're going from on line 3 phi y on line 2 phi y to line 3 for all y phi y, if that's what you're doing, you'll notice that actually phi y, it's all right, let me erase this little bit here. So this should be phi a. I'm going from phi a to for all y phi y. And what you'll see is phi a here is RAA, where that A is this one here. So phi y then is the formula RAY, and that contains A. Okay, so that's not permitted. So in short, to keep yourself safe, there's a simple recipe is if you're going from a formula like RAA and generalizing to for all y something, you better replace all the A's with Y. So sure, we could go to for all Y, RYY on line 3 here, but we just can't go to for all Y, RAY. Okay, so let's see some more examples of this proof method and put to work. Okay, so here I have two premises for all x, if fx, then gx, and for all x, fx, and I want to prove for all x, gx. Okay, so my strategy here will be, I will try to pick an arbitrary thing A and show that that thing is G. So in the back of my mind at line 3, as I do the next thing, I'm thinking I've picked an arbitrary name A. I'm going to use what I see on lines 1 and line 2, lines 1 and 2, to infer things about this arbitrary thing A. So I pick an arbitrary thing A from line 1. I know that if A is F, then A is G. From line 2, I know that A is F. Right? A is this arbitrary thing. It's F. Then I can use modus ponens. And now finally have A is G. And now checking back, look at the dependencies. So the dependencies of line 5 are 1, 2. In 1 and 2, A does not occur. So just to make this totally clear, here, these lines, A does not occur here, A does not occur here. So therefore, I'm permitted on line 6 to generalize what I have on line 5. So I can go to for all x, gx, again, copy those down, 5, universal introduction. Okay, so everything is G. Okay, so now we have a case of a tautology. So this is something where we're going to prove something and end up with no dependencies. Okay, now the one trick in this case is the final thing we want to prove is a universal sentence. So my strategy is going to be, I'm going to try to prove an instance of this universal sentence with an arbitrary name, A, hoping the instance won't depend on anything, or that's my strategy, and therefore I can generalize. Okay, so how do I get an instance? Let's think about what an instance would look like. So the instance I'm going to aim for here, I'll write this in green to show this is like my goal. My goal is to get this FA, arrow, FA, or GA. If I can get that, not depending on anything, and certainly not depending on anything with A, then I can generalize. Now that's going to be easy to get. I'm just going now to assume FA. So that's my assumption. Then I'm going to do a disjunction introduction, FA or GA, 1, or introduction, conditional proof. FA gives FA or GA. So 1, 2, conditional proof. Now I have no dependencies because 2 only depend on 1. So when I do conditional proof, I get to take out the dependency on 1. So therefore, line 3 cannot possibly violate the restriction for UI. So I can put for all x, fx, arrow, fx or gx. So 3, universal introduction. Okay, on to a couple other examples. Okay, now we're going to show from a premise, which is a universal statement, a conclusion, which is not a universal statement, it's a conditional. So take note, the conclusion here, if P, then for all x, fx, is not a universal, it's a conditional. Since the conclusion is a conditional, I'm going to try the strategy of assuming its antecedent, P. So I'm going to assume P and then try to get for all x, fx. And in this case, I look back at line 1 and see, okay, line 1 tells me anything has the feature that if P, then that thing is F. So, and I'm going to try, once I assume P, to show for all x, fx. For that, it's going to suffice to show FA for an arbitrary thing. Okay, so my goal at line 2 is I want to show FA for an arbitrary thing. I'm going to use line 1 to get that. So I'm going to put P, arrow, FA from line 1, universal elimination. That's okay. Line 1 is a universal sentence. I can just take off the universal quantifier, plug in the name A for X. Now I can get out my FA. Okay, now looking back at lines 1 and 2, the dependency on line 4 depends on 1 and 2. 1 and 2 don't contain the name A, so now I can apply universal introduction to get for all x, fx. So 4, universal introduction, 1, 2, and then finally I can discharge the assumption on P. So in other words, I can put P in the conditional here. If P, then for all x, fx. No more dependency on 2, that's discharged. So that's 2 to 5, conditional proof. Okay, one more example. Actually, this is just the converse of the previous one. Okay, so what I'm going to show now is the conclusion of the previous one, which was if P, then for all x, fx. That gives me for all x in brackets, if P, then fx. Okay. Pause for a moment and ask yourself, line 1, can I apply UE to it? So take a second to think about that. You might, if you don't know the answer immediately, pause the video and think, can I apply universal elimination to line 1? The answer is no. Line 1 is not a universal statement. Line 1 is a conditional. So do not try to just pull off the quantifier from the consequent of that conditional. So we're going to have to be a little more strategic with this proof. Looking at the conclusion, I know that an instance of the conclusion would look like this. So if I can get that, if P then FA, that doesn't depend on any dependencies with A in it, then I'll have what I need to do universal introduction. Okay, so here's what I'm going to do is I'm going to, trying to get that, I'm going to assume P. That's great because now I can get for all x fx. So I assumed P. For 1 and 2, I get for all x fx. Okay, and now I can just do universal elimination, get FA. Now I can do this conditionalized on P arrow FA. So 2 to 4 conditional proof. Now it just depends on 1. 1 doesn't contain the name A, so I can apply universal introduction. To line 5. So line 5, universal introduction. Okay, so in these examples, we learned how to use universal introduction. Universal introduction, in general, you're trying to show that everything has a certain feature. What you want to do is, in idea, pick an arbitrary thing and show that the arbitrary thing has that feature. In practice, actual practice, what you do in a proof is you make sure you aim to get an instance of the universal sentence, making sure you can get it in a way that it doesn't depend on any assumptions that mention the name that you used in the instance. Under those conditions, you can do universal generalization, universal introduction. In many cases of use of universal introduction, it will be very simple. It will actually just be, you'll strip universal quantifiers off from your premises. You'll do some reasoning. Then, because it only depends on your premises that are universal, you can put universal quantifiers back on. You can do universal introduction. In other cases, like the one we just looked at, it's a little more complicated and sophisticated. But as usual with all of these, practice is the key.